Hello everyone, my name is Fazil Ahmed and let's continue with our course of Continuum Mechanics. I am following Continuum Mechanics for Engineers by Mays 3rd edition. Today we are going to be discussing topic 3.10, the spherical and the deviatoric state of stress. Let us start with the spherical one first. The spherical state of stress is defined as that stress tensor which has equal principal stresses. This will be the representation of such a stress tensor. The principal value is called sigma m, where m stands for mean. But what is this mean of? What would be this sigma m equal to? Let us consider the actual stress tensor Tij. Its first invariant is given by Tii, or T11 plus T22 plus T33. The mean of these three values is the value of sigma m, and it is this and it is this representation. We can see it in another way, that the first invariant of the actual stress tensor and the spherical stress tensor should be the same, should be equal, and this is how we have defined sigma m. So what is the physical significance of this tensor? We will discuss at the end of the video. Next up, we have a concept that the stress tensor or any second order tensor can be divided into components as per our whims and wishes. We can divide a normal matrix into its symmetrical and asymmetrical part as per these formulas. Similarly, we have decided that we are going to divide the stress tensor into two components. One of these is going to be this spherical state of stress that we have defined, and whatever is left is called the deviatoric stress tensor. So the deviatoric state of stress is simply obtained by subtracting the total state of stress with the spherical state of stress, and it is represented by this matrix equation. However, we have to practice indicial notation and find a nag for it. So here is the indicial representation. Before we move, Before we move on to the physical significance, let's discuss some more math. What are the invariants of this stress tensor? Well, the first invariant is 0. We just replace j in this equation with I to get Sii, and it reduces to 0 simply. If we want to practice some more indicial notation, we can use this equation. We know from the previous chapter that delta Ii is equal to 3 when it is not sharing indices with anything else. That 3 will cancel this 3 over here, and tkk and tii are equal to sigma m, so it gives the answer 0. The second invariant is found by this relation usually. However, we see that in our case, the trace of the tensor is 0 because it is the first stress tensor. Lastly, the third invariant is always the determinant of the matrix, which cannot be further simplified, and it is shown here. Using these invariants, we write this cubic equation where S represents the principal values of the deviatoric stress tensor. But hold up, can we relate the principal values of the original stress tensor with the deviatoric stress tensor? Yes, yes, we can. For a normal stress tensor, we have this characteristic equation NQ, which represents the normal vector in one of the principal directions, and sigma q is the principal value in that direction. Let's replace Tij from this relation into this. Take delta ij common and see what do we have. We have a NQ, we have minus sign over here, we have a delta ij. We have Sij, which represents the deviatoric stress tensor, and Tij, which represents the actual stress tensor. It means that whatever we have in this bracket over here is the principal value of the deviatoric stress tensor in the q direction, or we can write it as this. Hence, if we know the principal values of one of the tensors, we can find out the other ones. Now, what does it all mean? Why are we studying this? We'll first try to relate this physically and find a sense for it. Look at this spherical stress tensor. This is just the identity matrix multiplied by a scalar. So, what happens if we take it through an orthogonal transformation? The answer is nothing. The spherical stress tensor remains the same, whatever orthogonal transformation you apply to it. To verify it, replace T here with an identity matrix and a scalar sigma m on the side. Multiply that identity matrix with A transpose and we get A transpose right back. Multiply the A transpose with A and we get the identity matrix back, because that is the property of orthogonal transformation or of orthogonal matrices. We multiply the scalar sigma m back in and voila, T bar is equal to T. We get the same stress tensor in a totally different configuration. This means that whatever direction we are looking at, for all directions on that body, the spherical stress tensor is applying normal forces on the body of equal magnitude. Or we can see it as the stress tensor can only change the volume of the body. It will either expand it equally in all directions or compress it. So we can say that the spherical state of stress is concerned with changing the volume of the body. Similarly, we can find physical sense that the deviatoric stress tensor changes the shape of the body. Now, I have not shown it here because it can't be shown for a general matrix per se, but the deviatoric stress tensor can be transformed in such a way that it only has shear components. The primary diagonal becomes zero. That is what we call a state of pure shear. What does pure shear do? It changes the shape of the body and only the shape. So the actual state of stress tensor, which will change both the volume and the shape of the body, can be divided into two components where each component gets one job. One state of stress changes the volume and the other changes the shape. Of course, this is an oversimplification. This is not why we have made this division, and this physical sense is not true for all cases. For example, orthotropic bodies will change shape by spherical. mm, for example, orthotropic bodies will change shape by the spherical stress tensor, and the deviatoric mm, stress tensor will change volumes in some cases. Also, the process of obtaining the matrix of pure shear is an iterative process. You apply transformations, see their impact, and iteratively get closer to a point where you see the normal stresses disappearing. So, why do we have done this division? This is useful in plasticity theory, where we discuss the behavior of the model separately for the deviatoric and the spherical stress tensor. Also, yielding and plastic deformation of many metals are essentially independent of this spherical state of stress. So we reduce our workload and complexity by focusing only on this deviatoric stress tensor in those cases. That's all for today. I hope that this video was helpful to you. If you liked it, please give it a rating. I'm just starting out, so any support you can give me will be massive. If you have any questions, just ask below and subscribe to show your love. Stay hydrated, stay safe, and I will see you in the next video.